All right, so on to our next example. Our next example is a little bit of an applied problem. So for example 3, we have that an object is propelled upward at an angle of theta to the horizontal with an initial velocity of v sub 0, which we also call v naught, feet per second. See figure 32. So figure 32 shows kind of how this is working. Looks like we're working with a cannon and a cannonball. If air resistance is ignored, so no air resistance, the range r, the horizontal distance that the object travels, is given by the function r of theta is equal to 1/16 of v naught squared sine theta cosine theta. So first things first, part A, we want to show that r of theta is equal to 1/32 v naught squared of sine 2 pi. Then for part B, we want to find the angle theta for which r is going to be a maximum. So let's start with part A. Part A, we want to show that r naught is equal to 1/32 v naught squared sine of 2 theta. So our goal here is that we want to get r of theta is equal to 1/32 v naught squared sine of 2 theta. We know that sine of 2 theta is equal to 2 times sine of theta times cosine of theta. And in our original equation, we have sine of theta times cosine of theta. So what we can do is we can rewrite the range expression with sine of 2 theta equal to 2 sine of theta cosine of theta in order to get this equation. But the only way that we're going to have 2 sine of theta times cosine theta is essentially going to be if we multiply by 2/2. Because remember, we have to, if we want to manipulate an equation like this and not have to change the other side, we'd have to multiply by an equivalent of 1. So if we did this, and we know that r of theta begins with 1/16 v naught squared sine of theta cosine theta. If we multiplied by 2/2 sine of theta cosine theta, what essentially happens is that our 2 in our numerator is going to stay put, and our 2 in our denominator is going to multiply to 1/16, which would then simplify to 1/16 times 2. So when we do this, this ends up giving us r of theta is equal to 1/32, or 1/16 times 2, of v naught squared times 2 sine of theta cosine theta, which now we know that this is just sine of 2 theta. So our equation simplifies to 1/32 v naught squared of sine of 2 theta, which is what we wanted. Essentially, we established an identity for this problem. This is exactly what we wanted, so part A is complete. Now for part B, we want to find the angle theta for which r is going to be a maximum. So we can first recognize that from part A, we can now find the largest value of the range in R. And to do this, we can identify that for fixed value of V naught, the angle theta, which we know is of inclination, the horizontal, which this just means that theta we know is inclined above the ground at some angle, determines the value of r. So this means that if v naught is fixed and 1 over 32 is just a constant, it's really just theta that's really affecting this equation. Now all we need to do is find the largest value of sine of 2 theta, which the largest value of a sine function is 1 at 2 theta equals 90 degrees. Since we're working with 2 theta, we know that our largest value of a sine function is 1 and it's at 90 degrees. But since we have 2 theta, this means that 2 theta is equal to 90 degrees. Then, if 2 theta is equal to 90 degrees, this means that theta is equal to 45 degrees for our problem. So this tells us that an inclination to the horizontal results in the maximum range. So for part B, all we really did was recognize that the only thing that really affects this equation is sine of 2 theta. We found, or just identified, that the largest value of the sine function is going to be 1, and it's when theta is equal to 90, but in our case we have 2 theta, so that means that our 2 theta would have to be equal to 90, which means that theta equaling to 45 degrees gives us a maximum range, which I actually realized I forgot to write the actual value in this last part here, so we're just going to scoot this over a little bit. So an inclination of 45 degrees, there we go. So now we can highlight our final answer. So that was all we did there in part B. So, all right. Objective 3, we want to use half-angle formulas to find exact values. So in equations 6 through 8, we can let theta be equal to alpha over 2. So equations 6 through 8 was this summary up here, which they're out of order. See, it says 7, 6, 8. But this just means that cosine squared of theta, sine squared of theta, and tangent squared of theta, for those equations, we're stating that if we replace theta with alpha over 2, we'll end up getting sine squared of alpha over 2 is equal to 1 minus cosine of alpha divided by 2. Cosine squared of alpha over 2 is equal to 1 plus cosine of alpha over 2. And tangent squared of alpha over 2 is equal to 1 minus cosine of alpha divided by 1 plus cosine of alpha. So then solving for the left sides of equation 9, we end up getting our half-angle formulas. So our half-angle formulas state that if we have sine of alpha over 2, that's equal to plus or minus the square root of 1 minus cosine of alpha over 2. Cosine of alpha over 2 is equal to plus or minus the square root of 1 plus cosine alpha over 2. Tangent of alpha over 2 is equal to plus or minus the square root of 1 minus cosine of alpha plus 1 plus cosine of alpha divided by 1 plus cosine of alpha. Then our plus or minus signs are going to be determined by the quadrant of the angle alpha over 2. So it's going to be really important for problems like these that we know what quadrant we're going to be working in, so we know what values are going to be negative or positive. We also have an additional half-angle formula for tangent of alpha over 2. Tangent of alpha over 2 can also be equal to 1 minus cosine of alpha divided by sine of alpha. which is also equal to sine of alpha divided by 1 plus cosine of alpha. So we have a few different equations for tangent of alpha over 2. I want it to be known that whichever equation that you use, it will come out to the same value. If you get an equation and you try each one of these, they may not come out to the same fractional value. You may end up with lots of square roots in different places. They may look different, but if you put them into a calculator and find their actual decimal value, you will see that they are the same. Just because they may not look the same by the different forms that you use doesn't mean that they are not actually the same value. Just want to make that clear. Well, let's go ahead and do example 4. So example 4, we want to use the half angle formulas to find the exact values of A, cosine of 15 degrees, B, sine of negative 15 degrees, and C, tangent of 15 degrees. So each one of these problems is actually going to take up a little bit of room. So we're actually going to write them horizontally instead of all vertically. So we're going to move some of these equations down a bit. So we're going to move this one right about there. And we'll move this one right about here. Just to give us a little bit extra room. So for A, we have cosine of 15 degrees. My screen is just freaking out. Give me 1 second there. All right, back to it. For part A, we have cosine of 15 degrees. We can identify that 15 degrees is going to be equal to 30 degrees divided by 2. Which when we use our half angle formula, we're using some angle value divided by 2. So this means that we use the half angle formula for cosine of alpha over 2 with alpha equaling 30 degrees. So 15 degrees is going to be in quadrant 1, which means that cosine of 15 degrees is greater than 0, so we're going to choose the positive sign. And we're going to need a little bit more room here, so we're going to scoot this down. So cosine of 15 degrees we know is equal to cosine of 30 degrees divided by 2, which using our equation is going to give us the square root of 1 plus cosine of 30 degrees divided by 2. Then we know what the value of cosine of 30 degrees is going to be. It's going to be square root 3 over 2, all divided by 2. We want to simplify this as much as possible. So if we multiply each one of our values here by 2, then we can get rid of our fraction in our numerator. So we're going to say we're going to multiply by 2 over 2. This would then give us 2 plus the square root of 3 over 4, which then we can simplify to say 2 plus the square root of 3 divided by the square root of 4, which we know the square root of 4 is going to be 2. So our value of cosine of 15 degrees would end up being equal to the square root of 2 plus the square root of 3 divided by 2. And this answer is very messy. It's really not uncommon for answers to look like this, since we do see that many angles in the unit circle will end up having square roots in them. And since our formulas for half angles are written in square roots, this is something that may come up fairly often. But all right, on to our next value, sine of negative 15 degrees. If we see here, there is a bit of a theme with the 15 degrees occurring. But if we have sine of negative 15 degrees, we really don't want to actually use sine of negative 15 degrees. We would rather have a positive angle degree, so we're going to use the even odd property to turn this into negative sine of positive 15 degrees. So we use even odd properties to get that sine of negative 15 degrees is equal to negative sine of 15 degrees. So we already have a negative on the outside of sine, which means that our final answer will have a negative despite what we already have for the positive or negative sign. We can very quickly identify sine of 15 degrees is going to be in quadrant 1. So for the formula, is in quadrant 1, so sine of 15 degrees is greater than 0. So for the formula, we pick the positive sign. But that's only for positive sine of 15 degrees. We have negative sine of 15 degrees, so this means that we're automatically going to slap that negative on to our final answer. So moving forward with this, if we have sine of negative 15 degrees, this is equal to negative sine of 15 degrees, which from our last problem, part A, we know that this is going to be the same thing as negative sine of 30 degrees over 2. So we're using what we've learned from part A to do part B. So we have negative sine of 30 degrees over 2, which we can now use our equation. So sine of alpha over 2 is equal to this positive or negative square root of 1 minus cosine of alpha over 2. So this means that we're going to get a negative, big parentheses, square root of 1 minus cosine of 30 degrees all over 2. So this means that we have negative square root of 1 minus cosine of 30 degrees, which we already found was the square root of 3 over 2, all divided by 2. So we're going to get a very similar answer here. So we have the negative square root of 1 minus square root of 3 over 2 times 2. We're going to multiply this once again by 2 over 2. This gives us negative square root of 2 minus, wrong color, 2 minus the square root of 3 over 4, which then we simplify to square root of 2 minus the square root of 3 over the square root of 4, which we know is 2. So sine of negative 15 degrees will end up being negative square root of 2 minus the square root of 3, all divided by 2. So, all right, let's just move this guy up just a little bit there and get started on part C. So for part C, we have tangent of 15 degrees. So we don't need to use an even or odd property in this case. We already know what cosine of theta is going to be. So we have everything we need to use our equation 12. So not using equation 13, just using equation 12, we have everything we need. Then we can just quickly identify that tangent of 15 degrees is going to be in quadrant 1. So it's greater than 0. And we pick the positive sign. All right, so we can go ahead and do this. So tangent of 15 degrees, we're saying is the same thing as saying tangent of 30 degrees divided by 2, which is equal, we're going to move this a little bit, which is equal to 1 minus cosine of 30 degrees divided by 1 plus cosine of 30 degrees. This is going to end up equaling 1 minus the square root of 3 over 2 divided by 1 plus the square root of 3 over 2. Now what we can do here is do the same thing as before, where we multiply by 2 in our numerator and our denominator, but still underneath our square root. And what we end up getting is one big square root of 2 minus the square root of 3 divided by 2 plus the square root of 3. Now this value, if we plug into a calculator, is going to come out to about 0.268. So that's what our first equation gives us. And just to go over the other two equations, we're going to do the other two equations as well and see that they end up with a different algebraic answer, but when plugged into a calculator, we get the same values. So let's do our next one. Our next value was going to be 1 minus cosine of alpha divided by sine of alpha. So this is equation 12. This was equation 12. So now we use equation 13a, so that first one. So tangent of 15 degrees is equal to tangent of 30 degrees divided by 2, which is now going to be equal to 1 minus cosine 30 degrees divided by sine of 30 degrees. This is going to give us 1 minus the square root of 3 over 2 divided by 1/2. So let's go ahead and divide the numerator and denominator by 2. This simplifies down to 2 minus the square root of 3 over 1, which just gives us 2 minus the square root of 3. So our answer in this case was a little bit more simple. So it's 2 minus the square root of 3, which, if we plug this into a calculator, gives us about 0.268. So even though they look different, this is going to be about the same. And let's do that last one. Let's do equation 13b. So if we look at these equations, we're saying that this is going to be equation A and this is equation B. So equation B is now sine of alpha over 1 plus cosine of alpha. So tangent of 15 degrees is equal to tangent of 30 degrees divided by 2, which is now equal to sine of 30 degrees divided by 1 plus cosine of 30 degrees. This is now going to give us 1/2 divided by 1 plus the square root of 3 over 2. And let's do the same thing as we've done every time now. Multiply by 2 over 2. And this is going to give us 1 over 2 plus the square root of 3. So once again, a very different algebraic value. But if we plug it into a calculator, this gives us about 0.268. So even though each one of these different algebraic values stemming from the different equations look very different, they all give us the same decimal value. So they are all equal. So this just goes to show that you can use any one of these equations and you shouldn't worry about it looking different or anything like that than a different equation. just know that it does come out to the same value. So all right there, that wraps up that last example and wraps up our section 7.6. So all right, that wraps up our last section for chapter 7, and I'll see you all again in chapter 7 review.